Okay, hi. Hi to the four of you. So I'm going to talk about protecting 5G networks against DDoS attacks, a case study in discrete optimization. So based on research I did at my previous university in France. I'm going to start by introducing like the real world problem that we're going to tackle, because it's going to make a lot more sense when we're going to talk about math later. And you're going to learn stuff about telecoms networks, which was not like the initial goal of the talk, but probably still not uninteresting. So the problem is like on DDoS attacks. So DDoS means distributed denial of service. And so you probably already heard of these because like they're a pretty big problem and also very widespread. So the idea is like you have an attacker, like called maybe a hacker, who like sets up a network of so-called zombies, which are basically like computers that he can access easily anywhere around the world. A lot of computers are left like unattended, and he uses them to like flood a website with requests in order to like bring it down. So you can have like tens, hundreds of thousands of computers sending requests at the same time to the same website in order to like crash it. And obviously this has like big consequences because they usually target an important company, and they demand a ransom in order to like stop the attack, because like obviously it has huge financial consequences. If you crash like a bank system, for example, it's a big problem nowadays. So like in this graph, it looks like all the zombies are sending the request directly to the victim, the victim target website. But obviously this is not like what actually happens in a telecoms network, because like the way it's structured is you have different access points to the network. For example, like 3G or 4G towers, or like your Wi-Fi box, loads of access points. And you have different like levels of rings of aggregation of this flow, and like sort of a backbone network with very high capacities, which means that basically when you're sending messages across the internet, the probability that you're going to stay on the access ring is very low. Like you're barely ever sending a request to a website hosted by your neighbor, right? So most of the traffic goes through the backbone network and actually travels like through lots of different nodes to get from like the source to its target. And so the counter strategy for dealing with telecom DDoS attacks, because obviously like the guys who operate these telecom networks, who like build them, like Samsung or Swisscom, anything, they want to prevent DDoS attacks because it's bad for their reputation if their clients suffer attacks. So the way they do it is they sample like packets, so like bits coming from all entry points over the network, and this allows them to detect attacks, because like this I don't know how it works, but you can like detect when something looks like a DDoS attack, like it doesn't look like a legitimate or valid request from a regular user. And when you detect such an attack, so you know, because like this packet contains the information of the source and where it's going, then you know where what is the target of the attack, and you know where the sources are. So what they do then is they divert automatically all the potentially concerned flow which could contain attacks to a filtering node, which is going to like look at every single bit and decide this is legitimate and this is attack, and I scrap the attack, and I let only the legitimate messages continue to the target through the network. So this is how it's done like nowadays. It works. It's pretty expensive, but it works. But with the move to 5G networks, there's something very important that's going to change and make this no longer possible. It's called network slicing. So slicing, most of the information is in the title. It means creating slicing your network into different layers that have different functions. Because the idea here, for example, we have the examples of like mobile broadband slice for your phones, or IoT slices. And the idea is that you sell a slice to a customer. For example, on IoT slice, you would sell it to, for example, Tesla for their autonomous cars. And this customer operates their IoT slice, their slice, the way they want. Like they have their own algorithms to route their flow. And it's no longer the operator, the owner of the telecoms network, who decides how to route the flow. Because and this is expected to be a pretty huge revolution and improve efficiency of networks a lot by being tailored to customers' needs. But this has side effects, especially in our case, because what this means is that the flow through the network becomes managed by the customer operating each slice. Like obviously they have a responsibility to bring packets from one source to a target, but the nodes that they go through on this path, they choose the path now, no longer the ISP, the internet service provider who built the network. So that means you can't do this technique that I introduced previously, where the DDoS attack, you would like divert malicious flow in order to a specific filtering node. You don't control this anymore. So you need a new defense system against DDoS attacks that doesn't rely on control of the flow in the network. And another thing that's going to change a lot with 5G is a new all-purpose tool for executing like network functions. For example, like I gave the example of firewalls, routers, like load balancing. Previously, you had hardware installed at specific nodes that would perform these functions. But today we have what we call virtual network functions, which basically is you launch a virtual machine at a node. You just need computing power to launch a virtual machine, which is like basically like virtual machine is like its own like computer without like a screen and everything. And this virtual machine can, for example, be launched in order to filter DDoS attacks. You can have specific software that does it, and you can do this at any node in the network where you can just launch a virtual machine and start filtering, right? So this is like a really powerful tool that is going to allow us to solve this problem in another way than, like in a new way compared to diverting all the DDoS attack to a specific node. So now I'm going to go to like the mathematical. Well, is this like clear, or like any questions already on the? Yeah, don't hesitate to interrupt me. Any questions on like the setup of the problem? And so now like we're going to like formulate it more mathematically and go towards solving it. So we assume that the target, sources, and the volume, like the total size of the DDoS attack, have been identified. Like as I said, I'm not an expert on how you identify what is an attack and what isn't. But we assume that this has been done. Our goal is to determine the optimal way to place virtual network functions at the different nodes of the network in order to filter all this illegitimate traffic while minimizing like the total cost it costs us, because obviously running a VNF on a network is has a cost. We also have like additional constraints. The main one being that we have a limited computing resource at each node in the network. Like it's not, even if like it's not so easy. You can't just like, if you identify the source, you just filter everything at the source because you don't have enough computing power at those nodes in order to do it. You have a limited computing power at each node in the network. You can't like launch 1,000 VNFs to filter a huge amount of flow at a single node. Yeah, because each virtual network function basically, it has a limit in the amount of flow it can filter, right? The speed at which it can filter is limited. So the question is, which paradigm of which optimization paradigm is appropriate for this problem? Like I give the example of reinforcement learning or like graph theoretical algorithms. Because obviously we have like a network graph that would make sense. Which one would be appropriate here? Do you guys think would we imagine like that reinforcement learning, for example, would be a good technique? Like anything like machine learning, like by like simulating attacks and looking at the results and changing the placement like that. What do you guys imagine? How do you guys imagine that works? No? Okay. Well, yeah?
I don't know, it seems you have a pretty solid mathematical formulation, so maybe more mathematical tools, like directly tackling it with graph theory, could seem more efficient.
Yeah, well, graph theory actually has its own drawbacks here, which make it not actually able to use graph theoretical algorithms, in the sense that graph theory deals very well with problems that can be expressed simply only on the graph, in terms of for example, if instead of placing virtual network functions at nodes and filtering a certain amount, we could just say we filter everything going through this arc in the graph. So all or nothing, we just remove arcs from graph. That's called network interdiction problem. Like when you say how many arcs do you have to remove for this attack to no longer be able to get there, then graph theory would be very well suited. But in this problem, we have lots of numerical parameters by how much we can filter at each side, the size of the attack, our computing resources, which make it impossible to use classical algorithms from graph theory. But reinforcement learning, yeah, it doesn't really work here because The main problem is that it's it's probabilistic, and there's like you have no performance guarantee. Whereas like this is fundamentally a security problem, and you basically want to guarantee that the attack is not going to get to the target. Because even if deploying virtual network, for instance, has a cost, this cost is nothing compared to the economic impact of a successful DDoS attack. So something that says most of the time we'll get a good solution is not acceptable for this problem. We want like a performance guarantee. And this performance guarantee is going to lead us, like as you said, to develop like a robust mathematical formulation based on linear programming. So linear programming is quite simple. It's not actually at its core programming, despite its name. It's basically an optimization problem that you can express as finding a vector that maximizes like C transpose X. So basically, like so in 2D, like AX1 plus BX2, for example, where A and B would be just real numbers, subject to a matrix constraint. So a linear constraint saying that a matrix product or vector is less than a certain vector. So basically anything you can express as a linear constraint, for example, yeah, the sum of all the x's must be less than 3. That would be a linear constraint, for example. There's lots of stuff that we're going to see next. That lots of stuff expresses itself very naturally as a linear constraint. And so linear programming is very nice because you can understand it very well graphically. Here you have what we call the feasible region in like orange or yellow, which is defined by all the linear constraints, which are the supporting lines of the segments forming the shape of this polygon. If we combine, like, we say that we have to be on this side of this line, this is a linear constraint. Like we're saying, this is expressed linear constraint. This is a linear constraint too. And you combine all these linear constraints. You say we want to be in all of them at the same time. That gives you a matrix constraint, and it gives you this feasible region. And here in red, you have like the objective direction here. So basically are characterized by this vector C that we said, the objective vector. And so you want to maximize in this direction on this feasible set, while the best point is right here. Yep.
So what you're saying, I mean, essentially is that also A is like a matrix of much lower rank than the dimension of X that you want to find in the line. So that's why you have all these lines that determine the simplex in which you want to use.
A lower rank. Well, here you have you'd have 1, 2, 3, 4, 5, 6. You'd have six. You'd have 6 rows for only 2 columns because you're in 2 dimensions, right? The number of columns is the dimension of your problem, and the number of rows is the number of constraints you have.
Yeah, I'm just saying that for the problem to be relevant, the matrix has to be somehow like highly non-invertible or something, so that you have this like simplex shape as a feasible set.
Highly non-invertible. Well, I mean, it's not square anyway, but we could talk about later. Maybe I'm misunderstanding your question.
No, it was just a remark.
Okay. Yeah. So that's basically the core of linear programming. It's called linear programming because the constraints are linear and the objective function is linear. Everything is linear in the problem. And there's a variant which is integer linear programming, which is much more difficult, but it differs only by the detail that our vectors, we're not looking for any vector now, we're looking for a vector that has only integer coordinates. And obviously like this complicates the problem because basically it means that instead of being a continuous space here, yellow, which is like, because the feasible set of a linear programming is always convex, because like you're intersecting like these constraints. Well, now you're only taking the integer points on, like, you have to imagine a grid here. You're only taking the integer points. And so obviously this makes the problem a lot more difficult because it now becomes like a combinatorial choice and you can't no longer continuous. But it still has a very nice like expression, compact expression. And we're gonna like, here we're gonna use linear programming, but we have the specificity that we're optimizing under uncertainty because like I said, due to like network slicing, we don't control the flow in the network. So we don't know how the flow will be routed in the network. And for optimizing under uncertainty, there's like 2 main big paradigms based on which is your like performance metric. If you want the expected best performance in a probabilistic sense. You want the expectation of your objective value to be the best. That's called stochastic optimization. And that's not very well suited here because, like I said, there's a very big imbalance in our case between the benefits of lowering the costs of deployment, which we want to do, and the catastrophic consequences of a successful attack. So since there's an imbalance, we don't want there to be a possibility of a catastrophic attack successful, even if it's a very low probability. We don't want that. So we're going to turn to robust optimization, the second big paradigm, which optimizes the worst case objective across all the possible scenarios that we consider in our uncertainty set. So that's basically that's how we wanted to solve the problem in order to offer a complete performance guarantee from a mathematical point of view. Yeah, so that's what I just said. And in our case, what is the uncertainty set? Well, we said that we don't know how the flow is routed in our network, the flow of attacks here. There's going to be a lot of complex notation here, but most of it you don't actually have to understand. It's an uncertain parameter, but we can narrow it down and define what it's actually can be, because there's two restrictions. Obviously, there's a bandwidth on each link, which means the flow cannot exceed this bandwidth. The attacker, whatever he wants to do, he's not going to be able to send more flow on a certain link in the network than it can support. And obviously, the total flow that is sent can't be larger than the total attack traffic. He's only generated a finite traffic, even if it's very high. And so that basically, these define an uncertainty set. And you might not notice it reading the text, but these are actually linear constraints. The total flow, so the flow routed across every possible path in the network concerning this attack, less than the total attack. This is clearly linear constraint. And the flow across on every bandwidth, on every link less than the bandwidth is also a linear constraint, because the flow from a different attacks less than bandwidth, and we only keep the paths that contain this link. So we have this uncertainty set characterized by linear constraints, and the formulation of a robust optimization problem in ILP looks like this. We have computing resource constraints as constraints number 2. Our objective function at the top. On 3 is this basically says that whatever the flow here, whatever the flow in our uncertainty set, we want to filter the total, we want the filtering capacity installed along the route of this, along the path of this flow to be more than its total, than what was sent by the attacker. And we're placing an integer number of filtering VNFs, virtual network functions, at each node. So I wonder, when you look at this, does anything shock you or surprise you? Abstracting from all the notation on the left, the Ks and everything, that's completely unimportant. There's something here but it's hard to notice. Well, what's wrong is this. This actually should not be in a linear program, because if you look at what this means, this uncertainty set, well, the flows that send less flow, send less than the total attack traffic, and with respect to bandwidth, there's actually an infinite number of these possible flows. Not just because there's lots of possible paths in the network, because they're still finite, but because you can this is continuous. It's not integral. You could send a little bit more on one path, a little bit less on the other, and so this is an infinite set. So it doesn't make sense to have a linear programming with an infinite number of constraints. We don't know how we don't know how to solve that, right? So what we're going to turn to is a specific method known as adversarial algorithms. And what this does is basically we're going to solve this problem by checking that generating iteratively new flows to add to this set U here. And when we guarantee that we can no longer find a flow which reaches the target, then we know that we're good, right? We have the best allocation. If we have an allocation which is like the lowest cost possible, and we can't find any way to route the attack to reach the target, then that means we've solved the problem. So it's like two steps which repeat in a loop. We calculate the optimal VNF allocation for the given uncertainty set at an iteration. Then we look for the worst case routing given this allocation. Like we say the VNFs are at these points. There's 2 here, 1 here, 1 here. How is the best way to route the attack in order to get to the target? And when this red problem here says I can't find any way to get to the target, then you know that you're done, because that means that your uncertainty set is the right one. It's still a finite size because you've done a finite number of iterations, but it solves the problem, and it's optimal because that's what we ask from the green problem. So this, the green problem, the optimal VNF allocation, is basically solving this with now a finite number of constraints. So this is an integer linear programming on a finite number of constraints. There are commercial solvers that do this very efficiently. So you don't need to worry about this. This gets solved nicely. Now, the red problem here, the worst case routing, given the VNF allocation, is a much more difficult problem. Why? Well, because our objective function is basically a maximum of a maximum. We want to route because of the constraints that the filtering, you can only filter the flow from attack if the flow from attack actually goes through this node. So you have constraints that depending on whether there's actually flow going through the node or not. Because in this case now your variables are no longer the VNF placement. This has been fixed, but your variables are the flow of each attack on each path in the network. And because of these this maximum of maximum, you have a binary variables equal in your problem. So you have these binary variables, these integer variables here. The main variables of your problem are continuous, but if you look here, you have one variable for each possible path of this attack for its source and its target in the network. And I don't think it's going to be very hard to convince you that if you have a network, the number of paths from point A to point B increases exponentially with the size of the network, not just linearly. Because every time you have as many choices as the degree of your node in the network, basically. So it gets very big, very fast. So this is not an integer linear program that can be solved efficiently by commercial solvers because the number of variables is much too high. So basically we have two problems here, the number of variables and integer linear programming, which mean that, and the combination is going to force us to adopt a certain resolution scheme based on classical optimization techniques. So first, let's tackle the integer part, the fact that we have binary variables. Well, this calls for a technique called branch and bound, which is extremely common. I'd say probably the most common discrete optimization technique, which basically means that you're going to iteratively make choices on your binary variables and view it as branches of a tree, because you start at the root where basically you've fixed none of your variables, and going down in the tree, branching, means fixing one of your binary variables to 0 or to 1. So basically each node has two children where you fix a new variable to 0 or 1. And when you get to the bottom, when your height is equal to the number of variables, that means that you've fixed all of them. And so you have an integer, you've fixed an integer solution, so you know exactly how much it costs, right? And it's called branch and bound because not only do you branch, because if you simply branch, you would enumerate all possible solutions. So 2 to the power your number of variables, that's way too much. But what you do is you evaluate a bound on the optimal value at each node. The classical way to do this is to relax the integrity constraints by saying that your variables here, which were either 0 or 1, they're now continuous between 0 and 1. Because, and obviously, since they have a bigger possible space, you're looking at you've made it continuous, but it's bigger, so the value cannot be worse than, it's only going to be at least as good as if you had only binary variables. So if the bound you obtain with this linear relaxation of your problem is better than your current best solution, then you continue branching, because that means you potentially can find a better solution when you go down. But if it's worse, that means that you've choices that you've made. Like here on x1, I said prune nodes because this means that just choosing x equals 1 and leaving all other variables free already leads to necessarily leads to a worse solution than one that we found elsewhere in the tree. So if this is the case, we know that we can just like stop branching, prune the node, and say we're not looking at any more at this search space, like because this choice already is like we know that this is bad, and this so you've cut into your search space just by doing this bound, right? So what this does is basically you cut branches of your tree. It's basically like if you have a tree that's getting way too big in your garden, you cut branches off, and this is the same kind of idea in order to reduce your search space and have a pretty fast algorithm. So we're going to do this to solve our program with these binary variables. But we still have the problem that we have an exponential number of variables. So actually calculating the linear relaxation at each node, calculating our bound, is a problem that is continuous, but with an exponential number of variables. And exponential number of variables are treated by a technique called column generation, which is like the go-to technique when you have linear programs that are too large for you to consider all your variables explicitly. The idea is, I'm not going to introduce the theoretical background for this because I think that would be like too complicated, but we can talk about it later if we want. But the idea is that iteratively, you find variables that have the potential to improve your objective function. Variables which, if you add them into your program now, you're going to get a better objective function. And so you do that, like you look for these iteratively, you keep adding them and looking for new ones. And if you can't do this, then you have like mathematical properties of like linear programming duality, which tell you that you know that if you can't find one, then there's no other one left. You have your set of variables currently, even though you've not generated all of them, is enough to get an optimal solution. And so your hope is that when you do this, you're only going to generate a small fraction of your huge number of possible variables here. So like what this would mean was basically for each attack at each iteration, you're going to find a new path which roots flow from the attack to its target. And you're going to generate, so you start with only like one path for each attack, and you generate new paths that are improving, and eventually there's going to be no possible like path because you're going to have enough stuff installed like to not find an improvement. And so like because of this iterative nature and the fact that you're like looking for new variables, it kind of looks like the adversarial method where we said we generate new flows in our uncertainty set. But I just want to warn you that it's very different in its theoretical basis, in the sense that here your guarantee of optimality of this of the correctness of the procedure comes from linear programming duality, whereas for the adversarial method, it's basically just saying if you can't find a flow that gets around this placement of virtual network functions, then that's exactly what you want. They don't have the same theoretical basis. So this gives us a complete procedure for solving the problem. We have this guy who we start with a reduced number of flows, and we iteratively generate flows through this adversarial method until we can't find a flow which reaches the target of the attack anymore. And in order to generate these flows, we call for a branch and bound method. To solve this problem, we call for a branch and bound method, where at each node we're going to execute a column generation in order to obtain the linear bound on these. To obtain the linear bound and hopefully prune our tree. So, in conclusion, we've learned about several paradigms today. Robust optimization, first of all, this idea of a worst case criterion for optimization problems under uncertainty, and methods to deal with this. So adversarial algorithms as our general framework, and specific methods of integer linear programming, and the techniques branch and bound and column generation. So I think this is a very nice problem in the sense that it really calls for a lot of classical optimization techniques combined in order to solve the same problem because of the very complicated nature of this problem. So thanks a lot for listening, and yeah, that's all from me. Any questions? Yeah?
Yeah, I do have a couple of questions. So first, the point of this integer relaxation
Yep.
is that there will be like an optimal point that would be, I mean, where the variable that you relaxed will be either 0 or 1, right? That's kind of...
Well, well, actually, it's a continuous relaxation of this problem, because this problem is integer, right?
Yeah, but I mean, isn't the point that when you turn to this linear program that then
Yeah.
is much easier to solve, then there is an optimum that will be such that all of these Z and A's are actually equal to 0 or 1?
Well, if that's the case, then that's like the best case. If that's the case, then if you find such a solution when you run your linear relaxation, if it turns out to be completely integer, the solution you get, then you're done. You don't need to do anything else, because you know that obviously it's also going to be an optimal solution if you only considered binary variables, right? But that almost never happens in practice.
So that's why you have to use.
So yeah, that's why you have to go, because if you found this at a certain node in your branch and bound tree, then that means that when your bound is equal to your current best solution, you say like I'm done here. So in your case, if it fixed none of the variables a priori, you would be at the root and find. Then you basically never have to branch at all. And even if you find one here, if you fix like 2 variables, and you find a completely integer solution, you know that like you're done at this, and you don't need to branch anymore. So that's really if that happens, it's very nice. But what happens more often is that you get like a discrepancy. You have some variables that are integer and some are fractional. And you choose a fractional variable, usually the one that's like closest to 0.5, because it's like the bottleneck variable, and you branch on that one again in order to get until you reach a bound that is worse, or you get.
Okay, so it's a bit like I think some algorithm for the knapsack program work like that.
Like lots of integer linear programs are solved this way, and yeah, knapsack problem is a classical one where you use this linear relaxation, which is super fast to calculate in order to solve the problem.
Okay, thanks. And I also have one other question.
Yep.
This set U of relations flows.
Mm-hmm.
So, I mean, it's a convex set, right?
Yeah.
So is it not the case that for a given, position of the branches, the set of, I mean, is it not sufficient to look at a bit like for this linear programming problem that you only look at the vertices of the simplex of the feasible area, right? Isn't there something a bit similar happening here? That kind of the worst flow in some sense would be an extrema of the feasible set, and so maybe you only have to look at finite values in some sense.
The worst flow will be an extreme of your feasible set. Well, you mean like why is the adversarial problem, the subproblem of finding these flows so complicated, right? Because
you said at some point that the problem is that you want to optimize that with respect to flow being in U, which is like.
Yeah, no, but the flow being U are actually the easy constraints here. Like the flow being U are the first 2 constraints, like the second and third line. First line is the objective function, and so these are the easy constraints. But the thing is, when you formulate the objective function first of all with only these constraints, it's a maximum of a maximum, and like it's in like a known proven property that it's maximum of maximum because like of this fact that you have this term on the right. If you take out the integer variables, it's a maximum of a maximum because of the idea that you can only count this minus what you filter if the filters are actually filtering something, right? Because otherwise you're not representing the actual cost of the solution if you're saying the total flow that I'm routing minus the total that it's filtering. This ignores the fact that the filters might not be at the right place to stop the flow that's being routed. And so you have to formulate as a maximum of maximum, and maximum of maximum is non-convex. contrary to, for example, maximum of minimum or minimum of maximum. And so since it's non-convex, you have like the mathematical property that you have no hope. Like if you formulate a maximum of maximum as a continuous linear program, there's a problem somewhere. Like because continuous linear programs being convex can only model convex objective functions. So we knew that our objective function was non-convex. So you know that you have to have some integer variables if you want to formulate it as a linear program. And so like we were hoping to get a reduced number, but we actually get a lot of different integer variables, like the number of nodes in the network times the number of attacks. That's like of sources of the attack. That's like it's polynomial. It's not exponential, but it's still a lot. And maybe there's a better formulation where with less binary variables, but we couldn't find one. Other questions?
Maybe I have another question.
Oh yeah, good.
More general one. So when you said at the beginning the different approaches leading to this problem, one of them was like machine learning, which
Yep.
wasn't very efficient. And I was wondering if it was not maybe like, in essence, it would not be very efficient because, as you said, you want to do like a worst case analysis, and then it seems like tools from machine learning are not really suited to
Yeah.
envision the worst scenario possible. And then you would have to resort to more like tools from optimization.
Yeah, exactly.
General thing.
Well, exactly, and I think that this is actually like it's a really important question, I think, in like optimization in general, because there's obviously a big movement towards machine learning and reinforcement learning because they've proven their efficiency on so many problems, and because they're able to treat such large scale data, we want to use them, for example, to control self-driving vehicles, right? But this is like this, but I think like the one big problem with this is you have with these classical reinforcement learning techniques, you have no provable guarantees on the performance, and I think that's a really big question for like the acceptance of like self-driving algorithms, because if they rely on reinforcement learning, you're not going to be able to prove how well they function, and we've already seen like accidents and stuff happening because of the probabilistic nature of these algorithms. So I think that's a really big question, but maybe some like technique which manages to combine the advantages of reinforcement learning, like is able to treat lots of data with a performance guarantee. Because like this still, I'm not saying this is perfect. I've not talked about all the problems this approach has. Notably is computation time. Because if we're combining so many techniques into one like resolution method, obviously this comes at a computational cost. You're doing lots of iterations of like linear program resolutions, and this takes a lot of time. So yeah, and especially like for this problem, you need a fast solution because you're responding in real time to attacks happening in a network. So obviously there's a trade-off between speed of calculation and guarantees of performance. Thanks.